manager who led engineering teams across Google, Meta, Amazon, and more, driving projects that touch petabytes of data and ship to millions. If you're not familiar with ACM, it's the world's largest professional organization for computing. We at ACM at ASU have a simple goal: connect students with real world insights, mentors, and mindsets that fuel impactful careers. This summer series brings industry right to your screen, and today's event is no exception. Without further ado, Karim Fatehi isn't just an engineering leader, he's a builder of systems and teams. At Google, he currently leads the Google Photos storage monetization business, managing at the intersection of scale, strategy, and technical precision. Before that, he engineered large scale cloud development at Meta, built analytics for Amazon's Echo ML platform, and designed full stack architectures for e commerce and media platforms at Google. Karim brings over 15 years of experience across the full stack of systems, from high level architecture and design trade offs to code quality, team culture, and delivery. Please give a warm virtual welcome to Karim Fatehi.
Thank you, folks. Sorry about the delay again. Apparently, the security was really tight and they did not let me in for a while. But thank you, Yash and John, for figuring all that out and letting me in. Also, thank you for the welcome. Happy to give a super brief intro. Yash already went into a little bit about my resume, but just wanted to share, um, I've been doing this I've been in the kind of software engineering manager space for the last 16 years actually now, coming up on even more. I graduated with my master's in computer science from UT Dallas in 2008, and then started working in the Boston area in 2009. Started out as an IC, worked for a couple of different fintech companies, went over to Amazon, started working on Alexa as an IC as well. Switched gears a little bit, went to being a manager at Amazon, and then when I went back to Google, I was an IC again, became a manager again, went to Meta as a manager, and then came back to Google as a manager. So I have a little bit of a history with both being an IC and a manager, and flipping back and forth, and spending the bulk of my time sort of building increasingly more complicated systems over time. Something about system design is it kind of appears and feels very theoretical. Even if you for industry hires, you can see a lot of the interview course material to train people for system design, and the examples used in there are pretty large scale systems, and it all feels very inaccessible until you actually get in there and start building some of these systems by yourself. And that could take years. So, my goal for today and my hope is that I can share a little bit about how you can get started with some very, very baby steps in this domain, because really the only way to build practical experience with system design is to build systems. So I want to get you started in the next 30 45 minutes in actually having a fully interconnected distributed system up and running on your computer. uh, it will appear very simple, and it does one very basic thing, but the goal here is not what problem the system is solving, but how to get started in the first place. So once you get there, you can add all kinds of complexity to it, and you will feel like it is all very accessible to you. um, so with that, let me go ahead and present. Host has disabled attendee screen sharing. I'm going to need to share my screen really quick. So if we can get me access to do that, that would be great. Um, okay, let's see if there's parts of this that I can talk about before we even get there. Uh, Hey, Yash, I don't know if you're still around, but if you could get me privileges to share screen, that would be great.
Sure.
You should be able to share now.
Okay, there we go. Chrome tab. All right, there we go. Okay, so we're going to bridge the gap between writing a single script and architecting a service or a system that could theoretically serve millions. Um, all of you are part of the ACM, so you're probably very familiar with algorithms of data structures, and you are, regularly writing code, managing projects, and the idea here is to take a collection of such simple projects and connect them together in a way such that you can basically scale infinitely. So to start, there's two kinds of mindsets. When we start out in computer science in college, typically what we start developing is a coder mindset. We focus on making a specific piece of code correct, efficient, bug-free, and that's really important. That's kind of the building block for all of this. It's like perfecting a single high quality gear. Um, and I don't want to minimize the importance of that. Without that, you cannot really get started. But I think all of y'all have already spent a bunch of time perfecting that. So, what I want to have y'all focus on a little bit more is how to be a systems thinker, how to be an architect, and look at the bigger picture. You're going to ask different questions. It's not just like, does this one gear work, but how is it connected to all the others? What happens if one of these gears fails? What happens if we suddenly need to handle 10x the load? Do we add more gears? What do we do over here? And can we do that in a way such that the users don't feel the system degrade over time? So that's the idea of systems thinking. You're thinking about the bigger picture. You're thinking about the sum of the parts, not necessarily each individual component with that much detail. Um, So what is a horizontally scalable system? So, maybe a phone is a really good example of something that is vertically scaling up every year. Every year, you get a new phone, it has more RAM, it has faster CPU, and it feels a little bit better. The screen refreshes a little bit faster, and you can play better video games on it. But in order to keep making it better, you have to do something called vertical scaling. You have to make this unit better and better and better. And if you compare a phone from now to like 10 years ago, it's a massive difference. But if you compare a phone from last year to this year, it's barely noticeable because we are beginning to hit a lot of just physical scaling limits on how much we can do with a single computer, right? So the way to infinitely scale out is to do horizontal scaling. And this is where you are architecting your code and your system in a way such that you can just add more computers when you want to process more. And these computers can still be the exact same computers. They don't need to invent any new technology. You just add more and you get more out of it. This is really how companies like Google, Amazon, Meta operate. We have huge data centers. If some computers in there fail, that nobody notices that. The world kind of keeps going. So let's come back to our practical example that we're going to build today. We're going to build a real-time like button. So if you've used Facebook or any other social media network, you know that there's a like icon, there's a favorite icon or whatever, and millions of people are using that icon. So what we're going to do is we're not going to build Facebook. We're not going to build YouTube. We're going to build a very simple system that just pretends like all it is doing is processing those likes for Facebook. And Imagine that this button may be available on like something like the Super Bowl ads website. What happens when 1 million people click it at the same time, right? If you have a vertically scaling system, that system is not going to be able to handle that many people clicking that at the same time. It will lose some of those counts. The performance of that system will be very, very slow. You could end up in a place where like your database just gives up. Um, but what we're going to build today is going to be able to scale very easily to any volume of traffic coming in. So that's the challenge we're going to solve today. So monolithic architecture, this is what a lot of companies got started on. Facebook got started this way. Amazon got started this way, where the user interface, the business logic, the data access layer were all combined into this like one giant server, which connected to this one giant database, and everything relied on vertical scaling. Um, if you kind of look over the internet, you will find, you can just search for like Jeff Bezos's service-oriented architecture email or letter memo. And you'll find that, a long, long time ago, Jeff Bezos basically like mandated Amazon to uh, not operate as a monolithic architecture anymore, go to this kind of microservice architecture, and that teams would be building services that would talk to each other. Now, at the time, it was probably overkill. It wasn't exactly necessary. Amazon was, doing its bookstore business fine, but Bezos had the vision and the insight to say like, hey, this is not going to scale one day, and one day we're going to need to be able to scale horizontally. And to prepare for that, we need to take the entire company and switch it to this microservice architecture. So this is a much more modern approach. We break our application into small independent services, each doing a very simple job. We'll have a front end service for whatever our front end is. We can have a system for processing the likes. We can have another for analytics. There's queues between them. All of these systems kind of behave independently. If one of them has a problem, systems that are closer to the user don't necessarily immediately start degrading. So you have a little bit of you have this option of being able to absorb some issues with some part of your system without it affecting all the other parts. So our system architecture is going to look something like this. We are going to have a very basic web application, which will expose a URL on which we will have people click their like. So there's no UI over here, but let's assume there was a UI and people click the like button. That like button is going to essentially fire off a request to a particular URL, which our web application is going to expose. That web application is going to be really simple. Its job is just going to say, hey, take this like and put it on a queue. Why do we have a queue? Because if that web application started updating the database, that would cause contention on the database. If too many people start clicking that request together, if the database is not sharded yet, we don't want to deal with any of those problems. So we're just going to put it on the queue, forget about it in the web application. It sits on the queue, and then there's going to be a like processing service, which is going to read off of that queue and then actually put things into the database. This can be scaled independently. The number of database shards can be scaled independently. So you're kind of disconnecting that from the user flow. And then once we update our database, we have an analytics service, which is going to read from that database and show that data to the analysts. Now, today we're just showing it to the analysts, but we could also theoretically like feed that back into our web page. So when you look at the Facebook like button, sometimes there's like a counter next to it of like this many million people have liked this particular page. We could very much connect different pieces of the system together to do things like that. Okay, so where's our data center? How are we going to build all of these things? Where are we going to put them? The answer is we're going to use Docker. So Docker is like your personal data center. You don't have to be an expert on database systems, data center racks. You don't have to understand any of that. Docker is a platform that will help you build and ship applications inside containers. Think of a container as a standardized shipping container. It doesn't matter what is inside. It could be a web server, it could be a Python script, it could be a database, it could be a queue. The outside always looks the same. So your container will run on your laptop, in the data center, on whatever machine, and the machine doesn't really need to understand anything about that container. So you don't have to do a lot of setup when you're working with Docker. You just have one Docker file. It'll work on your computer the same way. It will work on your friend's computer the same way. That computer may be a Mac OS computer. Yours might be a Windows computer. Doesn't matter. It'll all just work. And then we will use something called a Docker Compose file, which allows us to run our entire multi-container distributed system with just one command. So we will define a bunch of containers. They'll each be doing their small things. We'll bring them all together in Docker Compose, and it's off to the races. And that sounds very complicated. I actually did not start using Docker until 4 weeks ago. So how did I teach myself Docker? In the past, we'd have to get a book and go through the book and read some tutorials and watch a bunch of YouTube videos. And there was a lot of boilerplate involved in getting something like Docker understood and set up. But as of the last 2 or 3 years, AI has made this super, super simple. You can have an AI copilot that will accelerate your development, and you don't need to become proficient at some technology before you start using it. You'll have to become proficient at it over time to really build something more complex and deeper and be able to kind of scale that. But to get started, you don't really need to be proficient at it. You can just use AI assistants, and we're going to use or actually I've generated this entire guide using an AI assistant, and we're gonna fire it up. We're gonna launch it. We're gonna see how it works. But if you want to add more services, if you want to go edit something, if you want to understand something, you can have an AI copilot who will do all of that with you for you. So you can use tools like Gemini Canvas, where you can just ask it questions like, hey, give me this SQL statement for idempotent upsert. We're going to use that today. You don't have to know what that statement looks like. It will just give it to you. You can ask it how to configure your Docker files for your Python applications. You can tell it to put together the entire Docker Compose file. All of the code that you see today and you'll use today, none of it was written by a human. It was all written by the AI. I did go through it and make sure each and every piece worked as in, how my requirements were, but I did not have to write any of that code. And I'm not an expert on Docker, but I can use it. We'll also use Firebase Studio, which is an AI-powered IDE to do all of our running and building. And that is why you don't really need to set up your laptop in any particular way. You don't have to have any particular OS. You don't need to install Python. You don't need to install Docker. The guide does say install Docker, and if you want to run it on your own computer, and you're very welcome to do that, but you don't need any of those things. We can just have a fully functional IDE along with Docker in our browser, and it is just going to all work. And it's free, so you don't have to pay for any of this. Okay, so let's get practical. Our language and framework is going to be Python and Flask. Python's very simple and easy to read. Nobody even needs to know how to read Python. We'll just walk through the whole thing. Flask is a very, very lightweight web server for Python that allows us to expose an API. We're going to throw things onto queues that are inside Redis. Redis is a high performance memory queuing and database caching mechanism. So we're going to just use that. We're going to use Postgres to throw all of our likes data in there. And then obviously our containerization is going to be Docker and Docker Compose. So with that, I'm going to take us through a few short links, and I'm going to change our sharing module to actually just share the entire window so that y'all can see what I'm doing. Where's the share? Okay. you share? We are going to share this window. Okay. So if you want to follow along with me on your computer, please go ahead and quickly take a look at these links. Happy to keep putting them up there. If you wanna look at the link or something and you haven't recorded it down, you please feel free to raise your hand. I'm happy to take you back to the slide. It's a very easy link, electron.short.gy/guide, and that has the entire tutorial. If you want to use Firebase as your IDE, then you just swap the last three for IDE, and the entire code base is available on GitHub as a public repo, and we're just going to use that so that you have nothing to do to set up if you do /code in the end. So I'm going to start with the guide, and I'm going to walk you through this guide really quick so that you get a feel for what we're doing over here. So tutorial again, we're going to build a like system step by step. Prerequisites are Docker and Docker Compose, but again, you don't need that. We're just going to do that inside Firebase. So you don't need anything other than a browser. Firstly, we're going to create the project structure. So we're just going to make our folder. We're going to check it out. We are going to create some directories. We're going to have one for the web app, one for the processor, one for the reader, one for the load tester. We're going to simulate 1,000 users liking at the same time. So that is going to be a little load tester application. And then we're going to have the DB script as well. If you use this part of your script inside Bash, it is just going to help you create all of the files that you need and also make the project structure ready. Once you do that, your project structure should look roughly like this. We're going to go build out each and one of these folders as a component, put our Docker Compose together in the end, and then just script out a little bit. We don't really need that run.sh script, but we'll just script everything in there so that's very easy to fire off commands in here. Okay, so let's talk about the web app service. This is what we would expose to a Facebook application if we were part of Facebook, and it would allow the user to click on a like button and us to record it. So for this, inside the web app requirements.txt, we will use Flask and Redis. Flask is going to expose our API. Redis is going to allow us to, these, by the way, are Python dependencies. You put them in a file called requirements.txt. Flask is your simple HTTPS service. Redis is the Python library to talk to Redis. And if you look at the code over here, it is super simple. We are going to expose a /like URL. We are going to accept post requests to it. For our test, we are just going to take a post ID that is a random choice of post 1, 2, or 3. In a real system, this would actually have more URL parameters to it, to which post you're actually liking. But since we don't really have any of that infrastructure, we're just going to randomly choose between post 1, 2, and 3. We're going to push that onto Redis. And we are going to just return a log message, and we are done. All we're doing is pushing that like onto queue. That's it. For our web app, we probably want a health check. A health check is a way to help Docker understand whether your service is healthy or not. This is kind of the core user-facing part of the system. So we want to make sure that it is always healthy. So we are going to have a health check script that is going to just check the /health URL, which is also exposed inside here, inside Flask. And it is just going to make sure that we're getting 200. So if this server is not running, Docker is going to know that it's not healthy, and we can debug and deal with that. This brings me to the Docker file. The Docker file is a file that basically tells Docker what to do with the code in here. And essentially what we're saying is we are going to use the official Python runtime inside Docker. Our working directory is the /app. We are going to copy the requirements to that directory, and we are going to run pip install, which will install those requirements inside that Docker image. We're going to copy the rest of the application, and then we're just going to fire off app.py. So this is taking an existing Docker image from Docker Hub, making some modifications to inject our code in there, and then kicking off the script that will launch our server. Step 3, we're going to build a processor service. So very similar architecture. We put our requirements inside requirements.txt. We're going to use Redis, and we're going to use psycopg. That is used in order to talk to Postgres. We are going to read our queue. So in the main processing loop, we're going to read our queue from Redis. We are going to, if there's nothing in the queue, we're just going to wait. If there is something in the queue, when the connection presents a cursor, we're going to execute a very simple upsert query. So we're going to insert into the database for the particular post ID and like count a value of 1 if this is the first instance of it. Otherwise, we are going to do an update where we set the like count to like plus 1. So putting this entire thing into a single query gives us an atomic upsert where if the particular post ID already exists in the database, it increments it by 1. If it does not exist, it starts it out as 1. So because this is atomic, we don't need to worry about how many people may be clicking the like button at the same time, or how many threads may be processing that that queue at the same time. All of that will be idempotent, which is very important for distributed systems. Again, super simple Docker file here. We are going to, again, use the Python image. Similarly, copy the requirements, run the pip install, and then our command is going to be python processor.py. So our second image is ready. Then we need to initialize the database. So our database, if the table does not exist, we're going to create a very simple table. It has the post ID, it has the like count, it has a created at and an updated at timestamp. Usually good to have those on most database tables so that you know when things were created, when things get updated. And those are actually automatically dealt with by Postgres. So we don't even, it doesn't even show up in our upsert query over here. Okay. Then we have a reader service, which is where we take this data from this database and actually show it to our analysts. Again, that is going to be a Flask server because we need to be able to query it. And it's going to use the psycopg library to read from Postgres again. Again, really simple. We have a likes for a particular post ID. And what we are saying is get the count where that post ID is set to the post ID that was passed in, and just return that number. So we can just query for any post ID, how many likes does that particular post have? Docker file, exact same concept as all the other services. And then lastly, we're going to build a load tester service. This is going to simulate users. Now, we could go to web.5000/like and keep hitting like button ourselves, but that's kind of cumbersome. We'll do a couple of instances for our test, but then this will allow us to sort of simulate a pool of 1,000 users or 1,000 requests, and it will use multiple threads in order to really prove that our system is working asynchronously, and will run this load test for our application. Same concept for the Docker file. And then we want to bring all of this up together, right? We have made these individual containers that do small, simple things. We want to kind of bring up this entire system as if it were in the data center. That's where your Docker compose.yaml file comes in, where you specify each and every service you're running. So this is our Redis queue instance. This is our Postgres database. We need to specify some environment variables, like what is the username, password. We're going to use the defaults for everything, so there's no security in here, but that's okay because we're just building this application for fun. This is our web app. We're going to host that on port 5000. Everything is hosted on port 5000 internally using Flask, but we're going to expose it to 5001 so that we can have separation at the host layer. This is our health check script. We're going to make sure that things are healthy. This is our processor. It's going to build off of the processor. It's going to have the information of how to talk to both Redis and our database. So we're going to redirect it to talk to our database, going to give it the same username, password. Again, everything's default. This is our reader, same concept. Our load tester. And here you'll notice that it is under a profile called test, because when we bring up our system, we're not going to bring up our load tester. Our load tester we will manually kick off later. So we want to put it under a separate profile so that it does not fire off by itself. It will wait for us to go kick it off. And then here's a little DB resetting service that I have that allows us to just quickly, delete everything inside the database. That way, if we are like, okay, we ran a test, now we want to go clean up everything, we can just run that if we want. We're going to store the data inside a volume inside Docker. Docker, once you create a Docker system, you can actually define a specific volume that isolates that volume from the rest of your file system on the host. So you can kind of run things specifically just inside that Docker environment. And then we have this run script which exposes all of this functionality to us so that we can quickly run some of the things we want to run. So for example, once you build your Docker system, you're going to use a command like this, docker compose up. And we want it to be detached. We want it to build every time. We want it to use a scale processor of 3, which means we are simulating as if there's 3 instances running. But we don't want to enter that whole command every time, so that's going to just become start. Similarly, stop is docker compose stop. With teardown, where we just remove the volumes, we run our test. So all of this is just boilerplate shortcuts just to make our life a little bit easier so that we're not firing off these commands. And then step 9 shows you how to use the run.sh script in order to test out everything that we just talked about. But this is all great in theory, lots of steps. You don't actually have to do anything. We're going to do this live in front of you using the existing GitHub repo that has everything on there. So if you go back to our guide over here, we can just click on the IDE button, and it's going to take you to Firebase Studio, where if you're not logged in, you can go ahead and log in. Firebase Studio is one of those AI tools that I talked about, which will allow you to build sort of everything very, very quickly. Repl.it is another tool like this. If you want to use Repl.it, you can kind of play around with what works for you. If you want to do this locally on your system, Cursor is a good IDE to get started. But because we have everything ready and we just want to stick inside the browser, we're going to go to Firebase Studio. We're going to import repo and go back to our code over here and just copy our URL, paste it in here. This is the 3rd time I'm doing this, so I'm just going to call it like system3. We don't need mobile SDK support, and we hit import. And you'll see the magic happen right away. It'll take a few minutes to get everything set up. This is really like container inception, if you will. Firebase Studio is actually currently provisioning a tiny container for us to run, inside which we are going to run even more containers. So containers inside containers all the way down. While this sets up, I just quickly wanted to do a poll check for if anyone has any questions, anything that didn't make sense to them so far, or maybe it's too easy. I don't know. Just doing a quick check. Maybe we can use our reactions. So if you are, if you open up the reactions menu, just give me like a thumbs up if it all kind of is making sense to you. If it is not, then give me the thumbs down icon. If you're asleep, then give me the sleep emoji. Okay. For anyone who's following along or is doing this on their system at the same time, you would probably get to a window like this. You have Gemini on the right, so you can like ask it things like, "Hey, what does this project do?" And Gemini is actually going to tell you something. Contains a simple microservices application with a web front end, a reader service, a processor service, a database. It's a load tester as well for simulating traffic. So I did not give any of these prompts to Gemini. Gemini is just analyzing the code and doing it on here. Gemini can also do things for you. I'm going to not edit this code base right now just because I have it working. But you can actually ask Gemini to add new features over here, and it'll do it. So this is our structure. I just want to call out attention to one particular file that's a little important. Whenever you use Firebase, you're going to get this dev.nix file. And this dev.nix file essentially sets up your dev environment on a per project basis. So in our dev.nix file, what I am saying over here is that I want to use the 2505 channel for all of my packages. There's two packages that I really care about. I care about Docker and Docker Compose. This will make all of our system come together. And I use this line, services.docker.enable, as true, because if you don't put that line in, your Firebase Studio environment is not going to have Docker as a service. So putting this line in here allows you to use Docker. You can install whatever extensions you want, configure other parts. There's a reference guide to all of this inside, this URL up here. So you can go crazy about doing this if you're writing like a React app or something like that. Obviously, you'll see a lot of React stuff in here. But this line is very important if you want to use Docker. Okay, so all of our code is up and running. Let's go ahead and fire it up. So we can open a terminal and run.sh. Actually, let's just type out help just so we can see everything. Okay, so start, stop, check, reset. All sounds good. Let's go ahead and start up our data center. None of these Docker images are already available, so it's going to pull them down. This is not using your internet, it's just downloading them to the Firebase container, so you don't need to worry too much about network or anything like that. And if we give it maybe 30 seconds, it will have all of our services up and running. Maybe, yeah, I want to say less than 30 seconds. They're coming up right about now. Okay, so I kicked off my Docker start command. Theoretically, all these Docker services are running. How do I know? I can just type out Docker PS, and it will tell you all of the services that are up and running, what ports they're exposing, what are their names, etc. And we can actually go have some fun over here. We can go look at this this final button over here called Firebase Studio, and we can look at these backend ports down here. And you can see that a couple of these services are actually up and running. We can go to the one on 5001. This is our processor. Obviously, we don't have anything exposed on the main port. But if you type in health over here, you will see a OK 200. We can't really fire off a like over here because we have made that to be a post. But you could go and use something like Postman and just go manually call that URL if you want. We're just not going to do it over here just for time's sake, but you can do that. So let's go see what's in our database. Nobody has liked anything yet. So let's go see with using our check command, what do we have in our database? And you can see that, right now, post 1, 2, and 3 are all empty. Nobody has liked anything. Let's now use our like command to go like something. See what happens. This is going to bring up our load testing environment, and it is going to send a single like into our URL. And was sent successfully. And let's go check our database again. And voila. In post 2, we have a like. Now remember, our web app is very simple. It just randomly selects a post to go like out of post 1, 2, and 3. So in our instance, it has decided that post 2 is the one that needs to be liked. It has gone ahead and added that. This particular like went from that web app, from the load tester to the web app inside the Redis queue. The Redis queue processor took it out, put it into the database. Our database reader service has read that out of the database. So that like has made it full cycle in our system. So if we go back to this diagram, it has gone all the way from here to here. Very cool. Okay, so great. One person liked one post. Our system works. We were talking about scale and how it's infinitely scalable and how it can handle all of that. Let's do some of that. So let's type in test 50 over here. So we're going to do 50 likes. And this time it's a lot quicker because, Docker already has that image cached, and 50 requests were sent. Let's go check. Hey, 13 plus 22 plus 16 is 51. It's because we send that one like manually, and then we send 50 more. And now we have some distribution between all 3 of our likes. Apparently, post 2, the randomizer really likes post 2. But let's scale up even more. Why stop at 50, right? Let's go 1,000. So here we're gonna go all the way up to 1,000. It's gonna take about 7 seconds. Do 7.10 seconds. And now let's go check. 365, 354, 332. I'm not going to do the addition myself, but I'm pretty sure it is 1,051 at this point. If we go back to our diagram, all of these 1,000 have made it all the way through. And what is important over here is that our database upsert script was idempotent, which means that it is not going to overcount. Our queue system adds a layer of reliability to the whole system so that nothing gets dropped off. Even if the database is a little bit slow, every like has been accounted for. You could scale this to whatever number you want. If you truly wanted 1 million users to hit this, you could take this exact same Docker file, go to the cloud, go to AWS or GCP or any of these things, use their Docker configuration to set up 1,000 hosts that process this system, and now you'll be able to hit it with, million, 10 million likes at the same time. This is how large systems scale. So let's do a little bit of cleanup, right? Let's go. We said that we have a way to purge this database. What is it? Okay, so if we hit reset, we have truncated the table. let's go look at it truncated. There it is. It's empty again. So we have some good confidence that everything seems to be working. And you can go add a lot more systems if you want on here. There's no, you could add another service that actually exposes some posts. You can take that post ID and you can make it read it from the URL itself. There's a lot more you can do. If you're not sure how to do something, just press this button and you can ask Gemini to do something for you. Just for, testing sake, I don't know if it's necessarily going to work. We can say, hey, Gemini, today the web app randomly selects which posts to like. What if we wanted to read that from the URL and like that specific post between 1, 2, 3? Gemini can actually just change things away. You can preview that change. All looks pretty solid. Instead of randomly selecting, it is going to take it from the request arguments. If it doesn't have it, it's going to tell us that that post ID is missing. We could go ahead and update this file, and it is going to make these changes. Obviously, our like system is now not going to work. So if we go back to this and hit run.sh like, that might not work. I know it says successfully sent over here, but if we go hit run check. Okay, maybe it works. I think what might be wrong here is that we haven't brought down Docker. So we should hit reset and down. So it's still running our old code base. It has not updated what it is running over here. And tear down. Or down, I guess. Yeah, down tears it down. Okay. So now we can hit start again. And let's see if that like system works this time. So request one failed. And if we wanted to go look at logs, so we could do Docker PS. The name of our thing is going to be like system web 1. So copy that, Docker logs. So there was a 400, error 400, and that's probably this guy. Post ID parameter is missing. So now we need to modify our, what do we need to modify? We need to modify the load tester now to correctly include that request parameter. And there we go. It's going to alternate between all of these posts in there. So you get the point. You can actually, you don't need to. I'm not a Python developer. I did not know Docker 4 weeks ago, but I can start building all of this because the AI is going to do my work for me. So that's our presentation, folks. I'm gonna go back to these slides if anyone wants to take a snapshot of this code and go play around with it yourself. Go to Firebase Studio, very powerful tool. You can start building all kinds of apps without knowing how to build anything. And you can get really good at both app development, but also then system design from here. Okay, I'm gonna hand it back over to Yash to close us out, and would love to hear questions, comments, feedback, whatever you like.
Karim,
Yash, take it away.
thank you for your phenomenal walkthrough. The clarity, the depth, and the hands-on demo brought system design to life. We especially appreciate the time you took to prepare the documentation of and the walk through the GitHub repo. It shows how deeply you care about making this valuable and accessible to everybody. Thank you for going above and beyond. Truly appreciate you bringing the level of hands-on value to the community. Now, to kick off the Q&A, we actually have a few questions on our LinkedIn. John, can we have those questions, please?
I shared them with you.
Okay, so the first question we have is from Aditya Bora. How do you design systems that stay fast and reliable even when millions of people use them at the same time?
Karim, you muted.
Sorry, great question. Hopefully Aditya actually is here watching it or is going to watch the live stream later on. I think part of this answer actually I did try to address this, that one of the goals of horizontal scaling is to do exactly that. So if we look at our demo from today, you can spin up as many instances of that web app as you want, and you can actually increase that scale processor factor for the Redis queue to be whatever number you want it to be. So it is all about looking at your system, figuring out what parts of that systems are single points of failure that don't have any replication, and adding replication and parallelization to those, so that when you want to scale to millions of users, you just go add more instances, add more replicas, and then everything else falls into place.
Thank you, Kareem. The next question is from Isaiah Brown. He asks, how do you ensure the security and privacy of user data in large-scale systems that serve millions of users simultaneously?
Yeah. I don't know if I can do justice to that answer, that question in like the next few minutes, but I'm gonna take a stab at it. So I think what you want to do is, first of all, there are industry giants that have solved a lot of these problems for you. You can use systems like Firebase authentication, which will provide authentication by Google for your apps in there. Use systems like OAuth in order to use systems like HTTPS, TCP encryption, to solve a lot of these problems for you. If you try to invent these systems from scratch, chances are that you will run into things that are security vulnerabilities that you may not want to solve yourself. So use solutions that already exist. From a privacy perspective, I think something that's really important is any data that you're dealing with, you kind of want to think about it from two aspects. One is, why are you collecting that data? You should be able to explain that very clearly to the user, why you are collecting that data. So for example, Google Maps asks you for your location. If you read the prompt, it will tell you exactly what it is going to do with that. It is going to tell you how it's going to use it in the process of navigation and giving you directions, where it is going to be stored, how you're going to delete it. You give all of that transparency back to the user. So data is not a bad thing. And if you want to operate in a privacy-centric world, you need to give the user the clarity on how their data is being used. And then secondly, you want to pay a lot of attention to de-anonymization of that data. So if you and aggregation doesn't always de-anonymize, right? Like if you were able to say like, hey, there's actually like 50 people in this town, but I don't know where they are specifically, that still may not be de-anonymized enough. You may know exactly who those 50 people are because their addresses might be there in a public repository somewhere. So you really want to think about how are you going to, if you're going to use aggregated data, how are you going to make sure it gets de-anonymized properly? You got to pay attention to that.
Thank you, Karim. I had a question.
Yeah.
If you were designing a system today with scaling in mind, what's one trade-off you would make early that most beginners would tend to overlook?
Yeah, I think one very, very early trade-off is to prefer a lot of async operations over synchronous operations. You know, typically whenever an early sort of a coder mindset developer is starting a particular project, they're going to have things be synchronously blocking. You know, if you get a request, you actually write to the database before you return 200 on that request. That is, once you start building the system that way, it becomes very hard to later on build asynchronicity into that system. So from the get-go, you want to try and block as little as possible. Everything should be as async as possible, and then when you are approaching scale, your system will lend itself to that scale very easily.
Thanks for that. Now we'll open the floor for all of you. Feel free to drop your questions either in the Zoom chat or virtually raise your hand so you can unmute and ask your question live. Seems like we don't have any questions for now.
So I do see one as a direct message to me, and I'm happy to kind of ask that out. It is for an entry-level SDE interview at Google, what level of system design is required? So for an entry-level SDE role, typically we actually don't do a system design interview round. Typically, the system design interview round usually gets introduced when you are applying for an L5, a senior engineer role and beyond. The reason I wanted to talk about system design is, first of all, I understand that folks graduate out of school, they've spent a couple of years here and there, so not everyone who is listening to this necessarily is in college today. So I want to make sure that people who are even a little bit further in their careers have something to gain out of this. But more importantly, I think I wanted to plug AI-based development, which allows you to maybe ascend and become that senior engineer even faster, because you are able to jump from that coder mindset to that architect mindset even sooner. So I don't think that this presentation is very much geared towards like, this is how you're going to crack the Google SDE entry level interview. I think this is going to really sort of, how do you become an engineer that can continue to scale in your career many years down the line, what techniques you could apply. So that's kind of what my takeaway, or what I would love for folks over here to take away. Another question also has come in as a direct message. So my goal is to be a software engineer with a focus on ML, algorithm design and research. As a master's student in my last year, what should I be prioritizing topics and tools to land a role in this area? So I'm not an ML expert myself, but I've been dabbling a lot with like models on Hugging Face and Open Router and things like that. So I would start getting familiar with the open source ecosystem around ML and AI these days, and this is kind of where I think tools like Firebase Studio, tools like Google AI Studio, Cursor, etc., they can really up level what you do, because the bar the barrier to entry is very, very low now. You don't need expertise. I did not do a lot of ML in the early parts of my career. I'm beginning to dabble in all of these systems because whenever I don't know something, I just ask Gemini, like, hey, what is this thing? How do I connect with that API? And it will give me code samples and everything ready to go. So I don't need to, I'm not afraid anymore because I have that AI copilot with me at all times. So more than any one tool, I would say start using all of them. And when you can't, use your AI copilot to understand how you'd use some of these tools. Another one, as a beginner in system design, is it a good idea to first strengthen my understanding of operating systems and microservices? Yes, absolutely. I think without expertise, or not expertise, without understanding sort of like the core, snapshotting, checkpointing algorithms, what are deadlocks, how do you resolve them, atomicity, all of these concepts are very, very important to understand. And I think one of the things that I have experienced lately is that I learned all of these concepts in college, but then they kind of just sat there for a while. And now I'm actually finally reconnecting with these concepts because they come up in system design as I go around, working with my teams in order to design the systems. And building up systems, because it's so accessible these days, you can actually get in touch with those concepts on a practical basis much sooner than, a few years down the line. Okay, one more, and then I think we'll call it. What is my favorite AI copilot that I use the most in my daily job? I think, from a model perspective, Gemini 2.5 is very, very strong. Claude by Anthropic is also very, very strong for coding. I've tried a few different ones. Cursor is pretty good. But I'm poor, so I don't want to pay $20 a month. So Firebase Studio is a really good alternative. One of the challenges with Firebase Studio is it doesn't work on a local repo, so you kind of have to just throw things inside GitHub. But that's relatively easy to do. I've actually built a few iOS apps that way as well, where I'll just use GitHub to transmit my changes back and forth between my local box and my Dev Studio. So yeah, I think it's maybe it's a little less about like which model is ahead today. That ranking kind of keeps flipping all the time. So I would say try multiple ones. Use things like client bot inside VS Code or Cursor, and you can switch what model you're using over there. So you can try all of them. Sometimes some model doesn't get something right, but the other model really does, and you can kind of switch things around. Use Open Router to route your requests to different things. Be careful about setting up a credit card in some of these things because you can rack up the credits pretty fast. I had some free credits, but I definitely realized that there was, like, when I was playing around with it, there was an hour in which I exhausted like $50 worth of credits. So it can be expensive, but there's a lot of cheap stuff out there too that you can find your way around things. Okay, so thank you, everyone. We're exactly at 8:30. Yash, I'll hand it over back to you.
Thank you, Karim. Before we wrap up, I want to send out a massive thank you to you for spending this time with us and diving deep into what it takes to design at scale, lead with impact, and build systems that matter. To everyone who joined today, thanks for being part of this session and bringing your curiosity and energy. To stay updated, you can follow us on the links in the chat. If you enjoyed today's session, let us know and share your thoughts on LinkedIn or Discord. See you at the next one. Thanks again and have a fantastic evening.
Thank you. Bye-bye.